What we've been working on is easing the manufacturing of optoelectronic devices, in particular devices that either capture light, like a solar cell, or devices that use energy to generate light, which is more on the lighting aspect, which is using organic light-emitting diodes. These devices tend to be multi-layered devices, meaning that there's multiple active components that are stacked one on top of another, just like sheets of lasagna, and each of these layers serve a purpose to make the device do its job properly and more efficiently. So what we've been looking at is trying to find ways to make this in a very sustainable way. We're using vanadium oxide, and what we found is essentially we use a very simple method where we take the precursor, which is a commercially available vanadium containing compound, and we just coat it onto the surface of our device, and we just shine UV light on it. And what we found is there was absolutely no advantage and actually a slight device degradation by heating up the material. So this can now just be done on the bench, in air, no high vacuum, and no thermal treatment required. And we've demonstrated that we were able to implement this in a variety of organic photovoltaic devices as well as organic light-emitting diodes. So what the c.l.s data allows us is to actually understand what our starting point is, to understand how far we are from being a crystalline material, understanding what our oxidation state is, and essentially that gives us a much better understanding of what's going on and helps us to target and design future materials a lot better than just going in the dark and just trying stuff until finding something that works.